In this video, I talk about the symbolic solution of ordinary differential equations, or ODEs. It is based on my example script example symbolic diff. Let's start by putting a breakpoint in line 2, and now we are ready to start the script. Let's step to the first of the examples I've prepared. We set the default text interpreter to LaTeX. We set the default font size for the axis to 14. We define a symbolic unknown function, which is to be determined by solving the ODE. We introduce abbreviations for the first, the second, and the third derivative of y. We define some symbolic constants, which we will use as the coefficients in some of the equations, and we define a couple of integration constants, which I call C1, C2, C3. Now let's step through the examples. The first one is probably the simplest ODE you can imagine. It's linear, homogeneous, of first order with constant coefficients. So it's a prime plus b, a y prime plus by equals 0. We prepare values for the constants a and b, which will be substituted later on. And we have to give an initial condition, which in this case reads y at t equals 1 equals 2. We define a plot range and a string for the title of the graphical representation of the solution. So this is the definition part. Now we pass to the solution part. I clear the warnings. I open and clear a figure for the graphical representation. And I obtain the general solution of the equation in EQ by invoking the function dsolve. So this will give the general solution, which has the form you can see in the command window: C1, integration constant C1 times the exponential of minus bt over a. Let's check the solution by substituting it back into the equation. This should give a function that is identically 0. This is indeed the case. Now we can obtain a particular solution by giving the initial conditions, which you see displayed here, as the second argument to the function dsolve. So what does dsolve look like? This is the particular solution with the given initial condition. We substitute back into the equation and get again a function which is identically equal to 0. Now we look if there are constants which we can substitute by the numbers given in the definition part. So the function symvar gives an array of the symbolic variables that occur in the equation EQ. And now we substitute a and b, which are elements 2 and 3 in this array V, by our constants, and we get now an equation which does no longer contain symbolic constants. Again, we obtain the solution with initial conditions, and this is the solution, the particular solution with the given constants and the given initial conditions. Now we are ready to display this solution in the figure, and you can see it on the right hand side in the window of figure 1, a decaying exponential function. We can check whether the initial condition is fulfilled. Yes, the value at t equals 1 equals 2. Right, so let's step through the next examples. So the definition of example 2 looks like this. It's a linear homogeneous first order equation with non-constant coefficients. It reads at squared times y prime plus by equals 0. And the constants a and b will be substituted by 1 and 2. Let's continue to the next example, which is example 4. This is a linear homogeneous second order equation with constant coefficients. This is, of course, the equation of the damped harmonic oscillation. It has 3 coefficients. Now, 2 initial conditions. We specify the value of y and the value of y prime at t equals 0. So you see this particular solution in the command window and the graphical representation, the well-known curve of the damped oscillation in figure 4. The next example is a linear inhomogeneous second order equation with constant coefficients. This is the equation of a driven harmonic oscillator with damping, and the driving force has the shape of a sine curve. Again, we have 3 coefficients, 2 initial conditions. And the solution, the command window, and the graphical representation on the right in figure 5. We'll talk more about driven harmonic oscillations in a later video. Example 6 is a linear homogeneous second order equation with non-constant coefficients. It reads t squared times y double prime plus t times y prime plus 2 times y equals 0. There are no symbolic constants in this equation. We have 2 initial conditions, value of y and dy at t equals 1. And you see the solution in the command window and the graph in the window figure 6. Example 7 is a linear inhomogeneous second order equation with non-constant coefficients. It reads t squared times y double prime plus t times y prime plus 2 times y equals a times t. There is a single coefficient, symbolic coefficients in this equation. We need again two initial conditions. So you see again the solution in the command window and the graph in the window of figure 7. Let's carry on to the next example, which is number 8. This is a linear homogeneous third order equation with constant coefficients. We now need 3 initial conditions. We specify the values of y, y prime, and y double prime at t equals 0. These symbolic computations now take much longer than before. But eventually we will get a solution. So the solution is pretty complex. If we display it as a symbolic function, it's quite long. Okay, next example. Example 9. This is now a linear homogeneous third order equation with non-constant coefficients. The coefficients are sine of t for y triple prime and cosine t for y double prime. In this case, it turns out that dsolve is not able to find a symbolic solution. Well, this is rather the rule than the exception. You probably know that most ODEs, especially nonlinear ones, do not have explicit solutions in terms of elementary or even higher functions. I've passed the control to the keyboard by the function keyboard. Now let's continue and go to the next example. Which is example 10, the famous Bessel equation, which has a symbolic parameter n, which will then later set to 2. This is Bessel's ODE, t squared times y double prime plus t times y prime plus t squared minus n squared times y. I specify two initial conditions. And we get the solution in terms of Bessel functions. Please look up the Bessel functions in the help section of Matlab. We can have a brief look right now. So Bessel J is a Bessel function of the first kind, and Bessel Y is the Bessel function of the second kind. In the figure window number 10, you see a particular solution of Bessel's equation for n equals 2. Finally, we have Airy's equation, which reads y double prime equals t times y. There are no symbolic constants. We define two initial conditions, and the solution is now expressed in terms of Airy functions, which are a particular kind of higher functions. And you see in the figure window how this solution looks like. Okay, we continue now to the last example, which is a system of two linear inhomogeneous first-order equations. We define two unknown functions, f and g, and two equations. The first one reads f prime equals f minus 2 times g plus sine of t, and the second one reads g prime equals 2 times f plus 4g plus cosine t. We define two initial conditions. This means that we start this dynamic system at 0, 0 at the origin. The general solution is now contained in a structure with two fields. The solution for f has this form, and the solution for g has this form. We can substitute back the solution, the general solution, into the equations, and we get true and true for both equations. So both equations are fulfilled by these solutions. Now let's obtain a particular solution with the given initial conditions. So these are now stored in these function handles. Now we can plot the solutions. We can plot f and g as a function of t. So we generate a vector of t values, time values, and we display the solution as an animated line. We start at the origin, which is in the lower right corner of the figure in figure window 12. And we see how the solution evolves as a function of the time.